All right, so the last radical reaction we're going to talk about is allylic halogenation. Okay, so this is where we're going to halogenate an allylic position in an alkene instead of adding to the double bond. So we kind of talked about this in the first lecture as to why this might occur, and that's because that allylic carbon, this guy right here, right, the one that's one removed from the double bond, is quite a bit easier to homolytically cleave than is either the vinyl position or just a normal old secondary carbon, right? That allylic position is resonance stabilized, and so it can form a radical pretty readily. Importantly, right, why is that allylic radical so stable? Make sure you can draw these resonance structures. It is so stable because it is resonance stabilized, right? So that radical can come down and form a new bond with one of the electrons from that pi bond, breaking that pi bond in a homolytic way, creating another, just moving the radical, really. It's not like it's creating another radical, but it's moving it from one carbon to another. So the fact that that radical is nice and spread out through this network of electron orbitals is what adds to the stability of an allylic radical. What happens is when you take a bromine radical and react it with an alkene, you can get substitution on that allylic carbon. Okay, so now notice that I have my allylic carbon that has a new, carbon halogen, or specifically carbon bromine bond. Now, unfortunately, you can't just toss in Br2 and hit it with light in the presence of. You would get a mixture of the addition product as well. Right, we know that Br2 reacts with alkenes to form that addition product, right? That would not be a radical type mechanism. So in order to sort of ensure that we have these radical type mechanisms, we use something special, NBS. And I'm not gonna lie, there's a little bit of a weird trade-off in concentration that happens here. So you use a very tiny amount of NBS, and that ensures that you have this allylic addition instead of even a radical addition to the double bond. It just keeps the concentration of radicals very low. And the only radical that can form and stay there for a long time is the allylic radical, right? So if you did have a radical addition to the double bond, you would just end up getting elimination because you don't want to sit there. It doesn't want to sit there with a secondary radical like it would want to sit, like it'd be okay with sitting there with an allylic radical. The bottom line, if you ignore any of that I just said and just take in the fact that this is what I want you to remember. NBS equals allylic. Okay, it is a special reagent that is used specifically to generate that allylic substitution, right? Again, all it's really doing is creating a bromine radical. We have other ways of creating bromine radicals, but it does so at just the perfect concentration that leads to this allylic halogenation. So when you see NBS, you think allylic. That's my goal. Okay, and so what happens is you have this hydrogen abstraction, and again, it occurs at that allylic carbon because what's generated is that allylic radical. Okay, that allylic radical will then turn around and react with Br2, which has been formed in solution from NBS reacting with itself, and you will get a halogen abstraction. So that means that our radical is forming a new bond with one of these bromine atoms, and the other bromine atom is now accepting the role of the halogen. Okay, but this is now, most importantly, it's not the addition to the alkene that we just saw in the previous lecture. It's a substitution that's specifically happening at that allylic position. Okay. Now, what's important to remember about these allylic radicals is that they're resonance stabilized, right? So when we have this alkene and we react it with NBS, again, what are you thinking when you hear NBS or see NBS? Allylic addition. Okay. So that means that I'm going to have addition to this allylic carbon here. That is that product. But then how the heck did I get this product here? It's still an allylic addition, halogenation. Addition is not the right word for that. Substitution. But importantly, it's formed because of the resonance structures that you get with this allylic radical, right? Because the allylic radical will form on that carbon, but it's not going to stay there. You're going to have, it's going to come down and form a new pi bond with one electron from that existing pi bond, and that's going to cause a radical to form on that terminal carbon. Well, now this can go on and react with Br2 just like the other radical did, creating this product here, right? So this is what comes from this radical, whereas the first one came from sort of what I would expect given the original position of my double bond. But you're going to have to watch out for these resonance contributors and if they give you a different product, okay? That's not always the case, right? So in this first example here, either of these allylic carbons could have been substituted, and I would have gotten the same product. Likewise, if I formed a radical here and then had my resonance structure, well, the radical that I'm forming is also going to give me the same product because it's just a nice, neat, and symmetrical molecule, right? So it's not always that you're going to get two products, but you do always have to watch out for what's going to happen if that double bond moves, right? So you will always have to, when you're doing these reactions, generate your first expected radical, but then through resonance, move it over and see if you've gotten a different product, just like we did in this example here.